It's a pleasure to introduce Alastair Craw, and thank you so much for stepping in last minute. Who's going to talk to us about toric varieties and quivers? I don't actually have the title, so it's a change for me. Okay.
Got a really long title, so it's good to start early because then I can write it on the board. I'll do that and then I'll pick off. Right, so I'm told I don't need a microphone because it's all picked up around me. So do shout, anyone of course in the room and online if you can't hear. So hello, yeah, my name's Alastair. Thanks to the organisers. Vicky, I'm more than happy to step in. It actually means that I don't have time to get nervous before giving a talk. Doesn't matter how old you get, you still get nervous. Right, so the remit for the talks, I'm giving two talks. The remit is toric geometry and quivers. That could cover an enormous range of things. So I gave this sort of subtitle, which became the title, The Cox Ring of Quiver Flag Varieties. The plan is to focus on toric varieties, but to lead in towards the Cox Ring. So the first lecture will be largely toric geometry, but leading towards constructing the Cox Ring, or understanding how one should think about the Cox Ring and the implications for the understanding the geometry of the toric variety. And then the second lecture will lead in more to quivers or quiver flag varieties. These are examples of Maury dream spaces, so we naturally move for the first lecture toric varieties and the second lecture to a broader collection of varieties called Maury dream spaces. That's the plan. Oh, and I should say, so I'm aware that there are some genuine experts in the audience. Not that you'll need to look at this, but the lectures I'll give that there are lots of proofs and, so this is my website, the address is a little ridiculous, but at the end of it, MDS, Maury Dream Spaces, so there's a collection of notes on there where if you want more details on what I'm saying, there's all sorts of things there. So I'll begin. Have I forgotten anything to say? Yeah, let's kick off with, maybe I'll leave that there. I'll start just with combinatorics. And what I'll do is, so the plan is, right, so the remit is toric geometry and quivers, so the union of those things. I'm actually going to begin with the intersection. So I'd like to take a quiver Q. So this is nothing more than a directed graph. So a set of vertices Q0 and a set of directed edges Q1, and traditionally when one uses the word quivers, then to specify the head and the tail of each arrow, we use the head and tail map. So for every arrow we send it either to the vertex at the head of the arrow or the vertex at the tail. And while I'm here, I'd like to give you two free Z modules. So just the Z module freely generated by the arrows, and here chi A is some characteristic function, so just a formal variable indexed by the arrows, and similarly for the vertices. And again, the chi I's are just formal variables. So armed with this information, the key thing we need, and I'll try and emphasize that, so I'm beginning with a map of Z modules, and it's nothing more, so associated to the quiver, so it's the vertex edge incidence map. So for every arrow, I associate the difference, so the difference of the head and the tail. So if you like, this is nothing more than a matrix where the columns are indexed by the arrows, the rows are indexed by the vertices, and in every column I've got a +1 on the head and a -1 on the tail. One point to note, so since the sum of the coefficients here is equal to 0, you can see that any z-linear span of such things will lie in the co-rank 1 lattice given by having the sum of all variables equal to 0. And so if Q is connected, and here by that I simply mean that the underlying graph is connected in a natural way as a topological space, then this thing, so I'll call it lambda, so this is the image of the incidence map, is exactly the co-rank 1 lattice. I want to call them lambdas, don't I? Habit of a lifetime. It's the collection of lambdas for which the sum of the variables, sum of the coordinates, is equal to 0. So that's the image of this map. And so the way I've always found, where are we? The point then is we get the short exact sequence, and this is one of the key players. So here I'm building from a quiver or a directed graph to give this, but I get a short exact sequence. And I always refer to this as the Batirev-Cox sequence, or if I forget to attribute it to Batirev, as simply as the Cox sequence. This is the driver for everything in toric geometry. Here I'm beginning with a quiver to give myself a z-linear map, and so I've just fiddled things so I have a surjective z-linear map. But more generally, you can replace this by any surjective z-linear map where this is a finitely generated and free z module, and then you'll be able to play with toric geometry. That's the more general context that we might care about. But now let me roll back and just think from the point of view of quiver so I can draw some more pictures. And I'm interested in, so let's say as a fact that for all lambda in the image, let's call it lambda plus, of the sub-semigroup. So in the integers, I think of the non-negative integers, and I take the sub-semigroup. This is exactly the sub-semigroup generated by the chi-a's, so the direct sum of n's times the chi-a's. So for every such element, the set, so nq1 intersect the pre-image of lambda. So I've got lambda sitting in here, and I've chosen it to be in the image of the semigroup, so I'm slicing the positive semigroup in ZQ1. So this set is the set of lattice points of a convex lattice polyhedron I've got a habit of a lifetime of always calling these elements in this thing capital theta, and I've deliberately maintained I actually want this guy to be theta. Apologies. So the point is that when I'm keeping lambda general, I'll try and use the notation lambda, but the moment I pin a particular one down, I'd like to call it theta, if you don't mind. Sorry about that. So it's a set of lattice points of a convex lattice polyhedron. I'm going to call this guy p theta. Now, p theta lies in, well, it lies in the slice, and if I perhaps tensor this over the rationals, let's even say the reals, then I've got some affine subspace of RQ1. And so I can think about a polyhedron as sitting inside that rational slice, but it's natural to identify this with the corresponding slice. So we project down, perhaps I'll say an MR, which is M tensor over the integers with the real. So this is just R to the number of elements here minus the dimension of the corresponding vector space for lambda. So I say there's not a, so it's naturally up in ins inverse of theta, but I'm just projecting down or identifying that with ins inverse of 0, which is of course identified with m. So to do this, I mean, there's no canonical way to do that, so you know, there's not a natural origin in this guy, but anyway, I've got a convex lattice polyhedron that's this slice. That's the first observation. And the point of view that one naturally starts at often in toric geometry, rather than working with this sequence, which is the one that is very natural from the point of view that I'll go on to discuss, that one can take the dual sequence. So if I say, for any of these Z modules, I put upper check to mean hom from blank to Z, then the dual sequence, which I'll deliberately write backwards, so I'll deliberately write it this way. So this dual sequence, we have a polyhedron p theta, which I'm sort of thinking of as sitting in there. Tensor over the reals, and I've projected it down to there. Dual to this, inside n, or really inside n tensor r, so the inner normal fan, and I'll illustrate what I mean by this in a moment. So the inner normal fan of p theta in nr is or encodes the combinatorial data that we care about defining a toric variety. So one often starts with the study of toric geometry by considering cones sitting in a vector space and asking that cones, you have a collection of cones that intersect in a very nice way, and this is the fan, and this is actually going to sit in this vector space. But as I say, I find it very helpful from the point of view of geometric invariant theory to start with the dual sequence. Okay, so this is the setup from combinatorics. Misha?
What do you mean by lattice polyhedron?
So I've got a theta sitting in here. I'm slicing, so let's tensor over the reals. So I've got, when I tensor over the reals, this semigroup are the integer points in a cone, in fact, in the positive orthant, in RQ1. For our choice of theta in there, we're slicing that rational that positive orthant by an affine vector space, an affine space, and what we obtain is, well, certainly a convex polyhedron. Is it a lattice polyhedron?
It's not really rational, but it's not clear to me that, for example, the vertices are integral. Maybe it's true.
The question is, are the vertices all integral? In general. All right. We've got some experts here. Are these vertices always integers?
Is it important for the rest of
Oh, it's completely irrelevant. So,
Just a matter of. If you put rational,
you're certainly happy with the word rational. I'm certainly happy with that, but I think we... good. Okay, so let's give a key example. So I was umming and ahhing for a long time as to which example to give, and experience suggests I go with one that might be simpler than I might do. So I've chosen a genuinely easy one, which illustrates everything really very well indeed. And please, if you've seen this sort of thing a lot before, do calculate by yourself exactly this example, but stick an extra arrow from 1 to 2. So I will later in the talk about the quiver that has an extra arrow from 1 to 2, but I shan't do that for now. So here, the one with in white, so 4 arrows, is a perfectly nice quiver, and I'm going to index the arrows in a slightly perverse way. So I'm going to call them 1, 2, 3, 4, and we'll see why later. So for this guy, let me write down the shown exact sequence. So it said 4, let's make that a bit longer, mapping to, well, lambda, but let me break symmetry by saying, right, let's write down the incidence map. So I got 4 arrows. The first and the third are going from 0 to 1. The second is going from 1 to 2. And the fourth is going from 0 to 2. So there's my incidence matrix that's defining my surjective map. And as I've written it as a map to lambda, the point is, since lambda's corank 1, then in fact a very convenient way of breaking symmetry is actually just to ignore the first row. If we kill the first row, clearly we can reconstruct the first row by noting that you want every column to sum to 0, right? So you can uniquely rebuild that first row. So I've now got this map to lambda, and I've chosen a nice basis to do that. And while I'm here, I'd like to also throw in, let's also choose a basis on M. So you can see that the first and the third have a relation, and then 0, 1, 1, minus 1, adding up the second and third column is equal to the fourth column. That's actually a basis for the kernel. Okay, so that's my sequence. Right, so what I'd like to do is start slicing and looking at this convex polygon. So choose theta equals 1, 1. And I'd like to draw N4 intersect inverse of 1, 1. So it's the integer points in this convex polyhedron. The point is, so we just compute, we're just adding up columns of this matrix until I hit 1, 1. And it turns out that there are 5 points in N4 that map down to 1, 1. And if we choose one of them, and it doesn't matter, the point is about this identification with M, the identification with M and the pre-image of theta, there isn't naturally an origin, so you simply have pick any one of them. So 0, 0, 1, 1, the third and the fourth columns clearly add up to 1, 1. That gives me one of the lattice points in the pre-image. And now all the other 4 that I've calculated, I ask myself where they sit relative to this guy. So for example, one of the guys we can see, if I add on one copy of the first column here, which I'm choosing in my x direction, I add on 1 from the first row, and I subtract 1 from the third row, and it turns out that 1, 0, 0, 1 is one of the other elements in the set, add up the first and the fourth column, if clearly that's also 1, 1. And the point is that, imagine that we've already computed the 5 elements, and only after we've computed them all as a set, we compute where they sit relative to each other. So if I write them down, 0, 1, 2, 0, 0, 1, no, that's not right, 1, 1, 1, 1, 1, 1, 0, and then 2, 1, 0, 0. So imagine firstly that you've simply computed all 5 elements of that set. That's a genuinely simple calculation. But after the fact, choose one of them, look at the columns, the x and y vectors, and arrange them appropriately. And that, and only that, is what tells me where these lattice points sit relative to each other. That's our convex polyhedron. So this is p theta. Okay, so dually, I have our sequence from Z4. Here I've got this matrix that I computed earlier. I write down its transpose to get the dual sequence 0, 1, minus 1, 1, and 0, minus 1. So I've simply written down the transpose of this matrix, and I could go further. Let's at least stick this guy in. The inner normal fan is so rather than defining the inner normal fan, let's give you this as an example. So here I have my polyhedron. It's actually a polytope. In fact, it's a polygon. For every supporting hyperplane, I write down the primitive inward-pointing normal vector. I have those 4 vectors. They're all vectors in the dual vector space, which is, of course, this picture is happening in M. Then these vectors are happening in N. Let's write these vectors down. The inward-pointing normals are 1, 0, 0, 1, minus 1, 1, and 0, minus 1. So these vectors are V1, V2, V3, and V4. In fact, of course, all I'm doing is writing down the columns of this matrix. So in this very special situation where I've chosen a construction such that M has rank 2, in which case the fan is sitting inside this 2-dimensional vector space. This picture is happening inside NR, and this one is happening inside MR. Then because this has dimension 2, writing down a fan, so a collection of cones that meet very nicely, it's all determined by what's happening to the 1-dimensional cones, and in particular by what's happening to the columns of this matrix here. So if we add in the blue, there's an extra arrow. We don't change the incidence map at all, except we add in an extra vector that looks like this. So there's a 5th column that looks like this guy. Then the kernel is, of course, rank 3, and then just writing down what happens to the 1-dimensional cones doesn't specify the fan. And so that calculation I might get to at the end of the lecture, just to draw 1 or 2 pictures there. But this is an example of this fan. So this, and I haven't defined fan, but let's see, just say the words. It's a collection of cones of rational polyhedral cones with nice properties. With many nice properties. So it defines. So in this particular case, it specifies F1. So by definition, this is the projectivization of OP1, direct sum OP1 of 1, or if you like, the 1-point blow-up of P2. But that's the combinatorial side of things. That's how to build, firstly, the rational polyhedron, the lattice points in there, but the fan itself. I'm asserting that this fan defines this variety, but I'd like to give more justification about that and more explanation. But as I say, those who... So that's the combinatorics. Any questions at this stage, folks? Jesus.
You get some equivalence from the quivers to, I guess, projectively normal varieties.
Say again?
Do you get some sort of equivalence between your quivers and projectively normal toric varieties, so that you can start thinking of quivers instead of toric varieties?
Equivalence would be too strong. So here I'm just using the quivers to illustrate the construction. It is worth saying, yeah, I said, but feel free to replace this by any surjective Z module. It turns out this will be projectively normal. It's not clear to me that that's an equivalence, that every projectively normal toric variety arises that way.
As you recover all toric varieties. Do you recover all toric varieties this way, or you're not sure?
Which way? So the question is, do I recover toric varieties this way, but I'm not sure what you mean.
So you can start with a toric variety, any toric variety that has a polytope, associated to it,
Huh?
and then find a quiver.
The answer is no. So the question, given a quiver I've constructed a toric variety, it is not true that every toric variety comes from a quiver. Excellent. So I'm just using quivers to illustrate, or to put it another way, take any surjective map of Z modules where this is free and finally generated, you get a toric variety, but it's not true that every such map comes from the incidence map of a quiver. So that's really important. Thank you. Yeah, the quivers at the moment are just for illustration, but that's the part I'm going to go on and generalize. Okay, so that's the combinatorics. I want to do some GIT. Now, my talk was going to come after an introductory talk on GIT. But since I didn't know what Joshua was going to talk about, I'm going to give you exactly what I need. So Joshua, you now have to modify your talk in real time to take account of this. No pressure, my friend. Right, so I'm interested in building some algebraic geometry from this. So I want to take the semigroup algebra determined by this semigroup, NQ1, which is nothing more than a polynomial ring with one variable for each arrow. But to be clear what I mean by this, that every element of the semigroup, here I'm choosing 0, 0, 1, 1, and in this case N4, as in this example, this first guy I started with, these just turn into the exponents on a monomial. So this is nothing more than x3, x4 in this polynomial ring. So that's my semigroup algebra. This setup, and really the choice of the map ints, gives a grading. So the map ints defines a lambda grading, where for each variable, every variable is indexed by an arrow, so the degree of the variable is nothing more than the element of lambda, which is this difference, well, the image of the corresponding characteristic function under the incidence map. So what this does for us, I can freely use all the boards. Could you, this is, if this causes a problem, yeah, shout if I get too low. Or shout before I get too low. Right, so we obtain a grading of this ring by elements of this group where this vector space, so this vector space here has k basis the set of lambda semi-invariants. So this is the k span. You know, this is of course a ring. Each of these guys is itself a vector space. It's the k span of the semi-invariants. So of this important set, NQ1 intersect inverse of lambda. So while this picture, at this point we think we're doing combinatorics, and of course here we are, but this is actually giving us a k basis, these 5 elements, that give us a k basis for one of these vector spaces. Okay, the moment I have an algebra that's graded by lambda, so this is equivalent, and suddenly we bring in some geometry, this is equivalent to us having an algebraic action. This is, after all, a workshop on group actions. So an algebraic action of the algebraic torus, here I'll call it T, so again this is the torus whose coordinate ring is this semigroup algebra. Now lambda is co-rank 1 inside ZQ0. So this is an algebraic torus whose rank is equal to the number of vertices minus 1. So all right, this is k star to the Q0 minus 1. An algebraic action of this torus on, well, on this guy, so on the affine variety, indeed the affine space, whose coordinate ring is this semi-group algebra. So this is the key passage from, well, the combinatorics to the algebra and then to the geometry. So just for, in this example, just to make it very, very explicit, for our matrix, which is here, sorry, I lost it. For this matrix, the columns of that matrix are giving us the group action, right? So here, our group, oh, I think I want to, maybe I want to call them G's. I'll keep them G's because I've probably got, one of the problems with, I should warn you, right, quivers, the head and tail maps, often called the source and target. T, you've got to be really careful what T denotes, so let me not use T for something else. Tail, of course, and target play quite opposite roles. So let's have the elements of the group being G1 and G2 acting on, well, we're on 4 space, and so it's just a column. So the first column is 1, 0, the second is -1, 1, the third is 1, 0, and the fourth is 0, 1. So explicitly, the matrix gives us an action of this algebraic torus. And so now I'm in a position, I'll give then the key definition of the GIT quotient, but then, so here I've got this torus acting on an affine space, and I'd like to create quotients, and for this I'm going to pick a character of our torus. And not just anyone, I'm interested in theta being in lambda plus. In lambda plus, it's the image of this sub-semigroup. The point about picking something in lambda plus is if I pick something outside of lambda plus, this set will be empty. So I'm going to pick something in lambda plus. So then the toric variety, and I'll deliberately add in the word quiver. The toric quiver variety associated to, and let's say at the moment, the information I'm really using is this incidence map, which is driving everything, together with the choice of theta, is, so I'll call it x theta. The notation is AQ1 / theta t, but what does that mean? So what I've got this grading of this polynomial ring by all elements of lambda, but having picked a theta, so one particular guy, I can choose particular slices, and indeed the slices I'm going to pick are multiples of so j theta, I shan't write any further down in that board, j theta. So for our choice of theta, I take all positive multiples of this j, then to create this bit in the brackets is a z-graded ring, and then I can take, or a graded ring in the classical sense, and then I can take proj of it, but much of what I'm going to go on to talk about very explicitly is what this means. If I'm going to define for you a variety, a natural hope is to be able to say, right, what's an affine cover? How do I understand that variety very explicitly? So I'll go on and do that using this polyhedron. So this is the variety, and whatever it is, it's projective over x naught, which is spec of the torus invariance. So computing the invariant part for an action of a group on, in this case, a polynomial ring, is in general an extreme, I mean, it's sort of the motivating question underlying invariant theory, and so I just missed the erasers for a moment. So what have we done? I'm claiming that we've got a variety that's projective over some affine, just to say, so in our case, well, I'll write this down in just a moment. So to come back to Jesus' question, I put quiver there in blue. Oh, it's the blue even legible. So quiver here, I put quiver in brackets simply because if you replace ints by any surjective map of lattices, then of course the quiver disappears, but you can do this construction to obtain something that I'm calling a toric variety, and it turns out that every toric variety that's projective over an affine can be constructed in that way. So this is just illustrating the general setup. Yeah, so there's 3 remarks I'd like to make about this definition. So firstly, it's projective over this this invariant ring, but if Q, the quiver has no oriented cycles, non-trivial, has no non-trivial oriented cycles, so you can't find a path, a collection of arrows that starts at one vertex and travels around and comes back to where you started. If Q has no oriented cycles, it turns out that this invariant ring is actually just the base field. So we're projective over spec K. In other words, our guy is projective. So x theta is a projective toric variety. So at least for the case of quivers, one advantage one gets is it's very easy to work out the situation where you are projective. Where does the word toric come from? So I'd like to choose theta in now. I'd like to write this as in the interior of lambda plus, but that's not a very good way of so let me say what I mean. Lambda plus are the integer points in a polyhedral cone. Think of that cone, and I'll draw pictures later on when I really work over the reals, and I'm actually interested in theta lying in the interior of that polyhedral cone in a real vector space. So then, in this case, then x theta contains, right, so it's a quotient of this affine space. Of course, affine space itself contains a dense algebraic torus. So under these conditions, it contains the quotient of the torus modulo the other torus. And for this choice of theta, this is an algebraic torus of dimension number of arrows minus number of vertices plus 1. If we're not in the interior, we can lose dimensions, and indeed, generally we do lose. Well, let's not say generally we do lose. But we may lose dimensions, and I'll show examples later on where our toric varieties have all sorts of different dimensions. Well, I mean, there's one obvious thing to say, that of course when theta equals 0, 0 is in lambda plus, and I've already said this is spec of a point. So clearly we can lose dimensions if we let theta to be anything in lambda plus. So x that contains this quotient as a dense open subset. So we know the dimension of this toric variety, and moreover, the action by this setup of this torus on itself extends to an action on the whole thing. And the action of this torus on itself extends to an action on the variety itself. And so now I should say that this is typically the definition we might meet when we first read about toric varieties. So it's a normal algebraic variety that contains an algebraic torus as a dense open set such that the action of the torus on itself extends to give an action on the whole of the variety. Question?
Yeah, so if you don't have it in this interior, do you still have this action?
So you've got the action, but this torus won't be of this dimension. So yes, the semi-stability that points will coincide that on the face of it you might not want to coincide, and so you'll lose some dimensions. And the final thing to say on this definition, the moment that we have a variety that has a group action, then it's natural to try and exploit that group action to try and learn something about the variety. And so one of the reasons that toric varieties maybe I'll keep that one for the moment. Are so well studied that we can understand lots of properties directly. So thirdly, the action of this torus allows us to understand the topology, for example. The topology of x theta via, in this case, a stratification into torus orbits, or the stratification into torus orbits, which here one can write as x theta, so a disjoint union of algebraic tori to the dimension of an appropriate face, where f is the face of this polyhedron p theta. So for our p theta here, so we have one two-dimensional face, which is the whole thing. So there's one copy of k star squared in our variety. There are four one-dimensional faces, so there are four copies of k star, and there are also four torus invariant points in the stratification. So this is a lattice point, but it does not define a zero-dimensional face, because of course it's general in this case. So there are, 9 torus orbits in that particular example of p theta. And just as there are 9 cones in this fan, I should have said that I drew the rays, but the fan is the collection of all the cones. So it's the origin, the 4 one-dimensional cones, as well as the 4 two-dimensional cones. Right, so I owe you, especially as the first talk, some understanding of how I'd like you to think about proj in this context. Which pictures do I want? You only live once, right? So this will give us a nudge towards understanding the proj and really being able to calculate. So I prefer the polyhedron over this one. So I would like to keep that picture. Right. So in this, so I like to choose generators. So in general, to understand the proj, I want to choose k-algebra generators. I'll list them as F1 through Fm of this graded ring that we wrote down a short time ago, NQ1 J theta, where J is overall positive integers or non-negative integers. And I'd like to define, so I want to work with the locus where none of those are 0. So I take my affine space and I'm going to call it the theta semi-stable locus. This is nothing more than, so the whole of the affine space, and I want to throw out the locus where all of them vanish, from 1 through m. And of course the analog that we all know very, very well is the construction of projective space, where if we have the entire polynomial ring for an action of k star on a vector space, then I can choose the algebra generators to be just the variables, and here I'm throwing away the origin when I do this setup. Well, now I'm throwing away the locus defined by the intersection of these. This locus I can understand as a union of affine varieties precisely because the complement of the intersection is the union of the complements. Nothing more than that. So what we get is that this locus is the union from 1 through m of the affine varieties given by the non-vanishing of a single fi. So each of these is nothing more than, of course, the locus, the complement of fi equals 0 in the affine space. This thing is equal to the thing I've just written down, theta semi-stable, and that sits inside, but of course in general is not equal to affine space itself. I've got my torus acting on here. This is a torus invariant. Each of these is torus invariant, and so we actually get, for each of these I can ask, how does this torus, the T, act on these affine pieces? I take the T invariance of these and I look at the union. This is what we mean by Proch. So AQ1, this is our x theta. So this is the setup in geometric invariant theory where I have some, in this case, an algebraic torus acting. I cover the complement of this locus, and then the guy I care about, this is the variety I'd like to understand, is covered by these. And this only helps if we can get a handle and understand what on earth this admittedly complicating looking algebra really is. So if you think about it, this is, so the thing in blue, I don't like blue. So this thing, well, yellow's going to be really visible, isn't it? So this thing is the algebra generated by, so I'm allowed, right? I'm allowed fi on the denominator, or indeed powers of fi. So I take fi to some j, and I allow any numerator, anything in this ring here. So g is a polynomial. But for this quotients like this to be invariant under T, I need the group action to agree on denominator and numerator. So Fi was chosen to be a generator of one of these, and so this is J. For simplicity, if I'm lucky and all these lie in the theta slice, clearly some of them may lie in, you may need to go to higher multiples of J to write down all generators of this algebra. An obvious example is the construction of weighted projective space, if that's something you've thought about. But in general, I'd like to say these are in J theta, but in fact I might not be that lucky. So I'll write may need a multiple. It just depends on which value of J over here F comes in. So we can at least try to get some handle on what these algebras are. And I want to illustrate this in an example, and by some unique quirk of fortune, my polyhedron is sitting here again. So I'd like to work with this same polyhedron. And I'm going to choose one of the FIs. Now, so in this case, we are lucky that all of the generators of this semi-invariant algebra in this context, they all lie in this J equals 1 slice. Or in other words, under this correspondence between lattice points in this picture and polynomial functions, all of these guys are, the generators are all in this, picture. So for this setup, so I've got the same, it's perhaps helpful just to keep it there. So on the face of it, I'm going to draw 5 of them. So this one is x3, x4. This is x1, x4. This is x2, x3 squared, x1, x2, x3, and 2, 1, 0, 0 is x1 squared, x2. So these are the guys that I'm going to list as f1 through f5. It turns out that this one's redundant, so I won't actually need that. in my collection of generators, but feel free to work with this if you wish. So for each of these, I just want to focus on one of them. So for example, suppose I work with F, so let's take F1 to be x3, x4. What this is saying is if I allow this F1 on the denominator, and I possibly work with powers, but I don't need the powers in this case, I want quotients where on the numerator I've got g something that's invariant. So certainly I can write down some functions that look exactly like this from this picture. Namely, I've got a collection of g's that all lie in the slice, and I have this f1. So for this guy, that one option, if I take this as my g, x1, x4, I divide by x3, x4, that's exactly the kind of function I'm writing here, and effectively I'm looking at the vector from this guy. I'm choosing this as my origin, if you like, by deciding to work with x3 over x4. Then I get one guy that's going to be in this algebra. Another one I can see I could throw in is the vector in this direction, x2, x3 squared over x3, x4. And on the face of it, I could start trying to throw lots and lots of other functions in. But just as this guy is the vector sum of these two vectors, and this guy is twice this vector plus one of these, I don't need to throw the quotients involving these two into my algebra, and indeed that turns out to be this algebra here. So this is, which is of course, that one can simplify it as x1 over x3, and then what, x2, x3 over x4. This is nothing more than a polynomial ring in two variables, and this is n4 localized by x3, x4, invariant under this torus action. So this particular affine chart on our variety defines an affine chart that, of course, is spec of this algebra. And we can compute and compute for all of these guys to understand exactly what our toric variety looks like and patch them together. It turns out that I'm saying this one's redundant, or at least if you write down this calculation for this particular variable, then the affine chart is contained in the union of the affine charts for these two adjacent guys. So that's how to compute. Any question on it? Any questions at this stage? So if you haven't met, so apologies to those who have met Proj before, but if you haven't, that at least gives a way in to thinking about Proj and calculating a given affine cover. So I accept that I cheated. I mean, of course, the first time one sees something, one should see examples for which everything works out nicely. If one does the quiver with 5 arrows, on the first picture I drew of a quiver, I drew a blue arrow diagonally as well that gives 3 folds, then the charts aren't all smooth on every one of the GIT quotients there. I might get to that at the end. Right, so one remark, I've said it, but I'll write it. I'm using quivers. Quivers are irrelevant. Just take any surjective Z-linear map. So all this works for any surjective Z-linear map. That's the first thing to say. I'll call it I, but this is the analog of the incidence map from Zn to some Z module lambda. And lambda doesn't have to be free, but you can. And the key thing is, and every. So I'll say every semi-projective toric variety. So this is the word, some use it, some don't, so let me try and popularize it, because it's helpful. Projective over an affine. right, every semi-projective toric variety.
I mean, don't you need an extra condition there? The torus itself is projective over N5, but you don't have surgicality.
To a point.
You need to have something like no free torus actions. That is equivalent to that extra condition.
The map I from Zn to just a point, so the free Z mod, just the identity element. But that surely defines the torus.
You don't have surgicality.
If lambda is a point, lambda is just the zero element. Oh, sorry, I'm letting you choose. Well, you can choose lambda and not the same lambda. You can, so yeah. So works for any surjective Z linear map where n is anything you choose, and this is any finitely generated Z module. But for example, just the zero.
And do you require lambda to be free?
So in general, not. So if you have a semi-projective toric variety, then, we'll see soon. So I'll make this look geometric. This is going to be the class group of the toric variety. And the class group can have torsion. Thank you. So every semi-projective toric arises this way. For some I, n, lambda, and a choice of theta. So I must admit, I learned this. There's a lovely paper by Michael Thaddeus, toric GIT, that I learned this from. But there are other sources. That's the first thing I wanted to say, and oh yeah, I've already said it. So you may have to replace theta by some multiple when looking for generators. But I've already said that. I thought I should say it. Right. So in the final 10 minutes, I want to talk about the Cox ring. You've seen the Cox ring. So the Cox ring is actually this ring here with its grading. So the Cox ring of a toric variety is the lambda graded ring that I've been talking about throughout. The key point I want to make now is this is intrinsic. So the final section is that, so the Cox ring, right, so the key, everything is being driven. The key here is the lambda graded ring, NQ. Now, I've started with this surjective map, but in the next lecture I'd like to break out of toric varieties. And the point is that starting with that map is not important, or at least we can reconstruct it if we wish. So let's work towards that. So I want to make lambda R be the vector space that I've already talked about at some point, Q0 minus 1. And I'm interested in the secondary fan. So the secondary fan in this setup, so it's in this vector space, is the common refinement of the cones ints of f, and now f possibly in bad form, I'm using for a face of the larger cone, the positive orthant in the cone with the vector space of arrows, for f a face. So we take all the possible faces of this positive orthant, we map them all down under this map, ints, and we take the common refinement of all those, and the support of this fan I'm going to call the effective cone. This is, I'll use the notation cone of these vectors, ints of chi a's, where a is an arrow. This simply means that the cone, right, the r greater than or equal to span of these vectors, this is in lambda r, of course. That's the thing I would call the effective cone, and I'm also interested in the movable cone. So I'm going to call mov is the intersection, so over all arrows of the cone generated by the vectors int of chi alpha, where alpha ranges over all arrows except one. And I think this definition needs two examples to illustrate it. So I just need to specify the kind of GIT parameters I care about. So firstly, the first example is the one I've been dealing with. In this context, my incidence map was 1, 0, minus 1, 1, 1, 0, 0, 1. I take these vectors and I write them all down inside lambda. So here's a picture of the two-dimensional vector space. Lambda, I've just written down the 4 column vectors of that matrix. The effective cone is the non-negative span of all these vectors. Like that. So the effective cone is the thing in blue. It's just the cone generated by all the vectors. But the movable cone, I'm taking the intersections of some cones, but what this says is that I run through all the arrows and I remove one of them. Let's do it this way. If I remove the first column, just ignore that, let that be the first arrow, I take the cones spanned by these. But since those two vectors are moving in the same direction, then the cone determined by this arrow is just the whole thing, and I'm going to take an intersection. So that doesn't help me. But now when I choose this second arrow, if I ignore that arrow and take the cone spanned by the rest, I get the positive quadrant. And I'm going to be taking an intersection, so my movable cone is going to be contained in the positive quadrant. That, of course, is the same as the first one, and if I remove this guy, I still just have the whole thing. So the movable cone is actually that cone where I remove the second arrow. In other words, it's this. So the movable cone is contained in the effective cone. How shall we? The second example I wanted to give, for interests of time, do you mind if I do something that, of course, my undergraduates will hate? If I throw an extra arrow in along there, I won't have the problem. When I remove this guy, I'll still have an extra arrow playing the same role. So in that context, the blue one actually has the movable cone equal to the effective cone. So there's a calculation one has to do in this setup too. And so what I'd like to do is I'd like to put up the main result, and then I will finish. So the main theorem, and this is toric geometry. I was asked to summarize toric geometry in an hour, and this is my attempt to do that. So let theta be in the movable cone, and let it lie inside or in the interior of a top-dimensional cone. In the secondary fan. You can see there are two secondary fans over here. One is the one I've drawn, and the second secondary fan is this, but there are two arrows shooting off there. So admittedly, those two examples are really quite samey, but that's the setup. So I'm only interested in something in the interior of one of these. So then, how to finish? So firstly, the point about this is that this map, theta semi-stable down to that constructed my x theta. So this is a geometric, is a really nice quotient, a geometric quotient. So the fibers are T-orbits. And if we don't sit inside a top-dimensional cone, then we might lose some of that. Secondly, x theta is, now, in general, it's a q factorial. But in my quiver examples, these are smooth, projective, toric variety. And the last half board that I'll pop here, this sequence that I've been writing down all the time, I refer to it as the Batirev-Cox sequence. So Cox exploited it a lot in his paper constructing toric varieties by GIT, and Batirev several years before in constructing Fano-toric varieties had used this. So the third statement is that this guy that was integral, no pun intended, to everything I've been doing is actually giving me a presentation, torus invariant V divisors of the class group of our toric variety. So lambda is the class group, and in our context, when it's smooth, this is actually the Picard group. And for every lambda in plus, this algebra that we have been looking at, this is the guy that's driving everything. These vector spaces. If I have lambda here, then this is sent to something over here, some element of the class group. I'll call it L lambda because I'd like to think of it as a line bundle. This is the cohomology of that line bundle. The space of sections of the line bundle associated to lambda in general, certainly when we're smooth. And so this Cox ring, this key thing, and this is the key conclusion, that this graded variety, so this graded ring, this thing that's driven absolutely everything is isomorphic to a ring that's encoded by the sections of the class group of our toric variety. The key word is, this thing that's driven everything is intrinsic. That information I can build, it's meant to be x theta. That I can build from x theta, geometric objects on x theta, and this is the thing that's done all the hard work for us. So it's intrinsic. Okay, I'll stop there.
Any questions? If not, let's tell you how you go. Yeah, so we have a coffee break for half an hour, and the next one's at 1:30.
I do have a question quickly. Alastair?
Hey.
Why is it called the movable?
So if we move to here, the lambdas are things in this lattice, so they correspond to, let's say, line bundles rather than. So they're exactly the movable line bundles. So some line bundles, every possible section has one guy that you can't move, right? So the point is that this guy, any section of a line bundle over here has to involve the divisor, the D2, the second of the divisors. No matter which line bundle we pick over in this part, as every section involves D2, whereas the others, everything over here, using linear equivalence, you can choose an alternative description. So yes, or really, the one I've described as the movable cone is the closure of the movable cone. So we'll see that in terms of the geometry. When I'll start tomorrow by doing variation of GIT quotient, and it'll give you, there'll be geometric consequences of that. Nice one. Freya.
In your theorem, if you remove the hypothesis that theta is in the movable cone, what part is great?
So if we're not in the movable cone, we're dropping dimensions. So what I was really gunning for, I was really gunning for this sort of corollary. So the point is, if we're not, we still get a toric variety, but the point is that we're sort of using the wrong GIT construction. And in particular, lambda isn't the Picard group. We've got something with too much information. In fact, this example illustrates it very nicely. So this F, if I pick something over here, here's the yellow's my movable cone. I pick something in the interior, I've got F1. If I pick a parameter even on this ray here, but certainly over here, I get P2. The GIT quotient, when I calculate it, is just P2, where of course the Picard group is rank 1. So I've got too much information, and so I'll lose this isomorphism. The point is just, and this actually alludes to what Johan was asking with his, sorry, you moved, about his question about having extra torus factors. That then we've just got too much information, and sort of we want a different GIT construction. In fact, here, if you just use a slightly different, if you like, a different quiver, if you take this white arrow and collapse it, then you get 2 vertices with 3 arrows, and then the GIT construction will give you a 3-dimensional affine space mod a copy of K star, and that's actually the P2 that you care about. So yeah, we've just got too much information here. That's a good question, thank you.